While both the standard horizontal dipole and the inverted V are half-wave wire antennas, physically dropping the ends to form the V shape changes how the RF energy is distributed. In real-world applications, especially on lower HF bands like 80 meter or 160 meter, where achieving a height of half wavelength is mechanically difficult, the radiation patterns of both antennas are heavily influenced by the ground beneath them. This visual will actually cover the difference between inverted V and horizontal. We'll see. Now, this is the pattern. The waves are going almost vertically upwards when the angle is 90 degrees. It's an inverted V pattern, and you can see it is near vertical incidence skywave enabled. And the antenna is at a very low height, just 0.1 lambda. That's when the antenna is lower, most of the waves go straight up into the sky, and you can have local contacts but not DX contacts. That is what we often call as cloud burners. It burns the clouds rather than getting your signal away. So 90-degree angle inverted V at a very low height, 0.1 lambda. Now if I increase the height, the recommended is, this is quarter lambda. It's a fairly good pattern, both horizontal and vertical are there. Still it's an inverted V at 90 degrees. And when it goes to 0.5, that's a very good pattern. Almost most of it is horizontal. Horizontal means low angle radiation. It will reach the ionosphere at a long distance, and then the reflected wave will also be at a very long distance. So this is a good position for DX contacts. And when it goes higher, additional lobes appear. See, there will be another lobe downwards also, which is a waste. You can see the additional downward lobe coming up. Earlier it was behind this lower lobe. That's why you didn't see that. And as the antenna becomes height is at full wavelength, you see several vertical lobes are coming up. So actually it is not an advantage to have the antenna at a very high location. If you are thinking of DX contacts only, this will be better because most of the waves are going horizontally. So it will be a DX contact antenna. This is all inverted V. Now you can see that NVIS is low because the signals are not going to the clouds. And see what happens when the angle is increased. When it's increased, you can see the angle here increasing. Upward radiation is increasing. See, this is going up. Part of it is going up. And when it becomes a true horizontal, that is 180 degree, means it is a horizontal. Still the NVIS is low, but there is some NVIS for horizontal antennas, dipoles, compared to inverted V. This is at 0.5 lambda height. If you decrease the height, it will again go into the mostly, when the height is very low, the radiation is low because ground absorption occurs. And when it is 0.25, it is almost vertical NVIS enabled, high NVIS. Local contacts are good, but DX contacts will be bad. And it will go up, and this is 0.5 lambda height. That is a half wavelength height. Again, as in the previous case, other lobes are appearing in different directions when the height increases too much. So the sweet spot for us will be 0.5 lambda and apex angle you see that up to 120 apex angle, the sweet spot for inverted V is 90 to 120. The pattern is almost similar if it is at a half wavelength. So the advantage of the antenna is when it's at half wavelength and 120. NVIS status low, inverted V, that means you have a good DX. 90 also, it's good DX. So 90 to 120 and 0.5 lambda will be the best for a DX contact. And another thing is that when you change this position, something which is not shown in this diagram is the change in impedance. When this is horizontal, impedance of the antenna will be about 70 ohms, while when it is 90, it will be about 50 ohms. So the matching and SWR will be better for a inverted V for a standard coax, 50 ohms coax and system. So I hope you have understood the physics or the radiation pattern of inverted V and horizontal dipole antennas. So next time you put up an antenna, think of all these factors. So this is the pattern when the antenna length is 0.1 per wavelength. That is 1/10 of the wavelength of the operating frequency. And as you increase it, now you can see this is a half wave dipole. The pattern has changed. As it is increased, when it goes to full wave, this is full wavelength. So you can see the pattern has changed like that. Now we'll see what happens when it goes beyond that. When it goes beyond that, you can see different additional lobes appearing here. Small additional lobes are appearing here. See, more additional lobes have come, and the amplitude of the additional lobes, and they are radiating in different directions also. 1.4 here, and the maximum amplitude also is lesser there. Now the additional lobes are more prominent than the original lobes. You can see the original lobes have become smaller and the additional lobes have become very prominent. See, at 1.7 times lambda, original lobe is very, very small. When it goes to 2 lambda, original lobe is not to be seen at all, but the maximum amplitude is good. This is what you think of when the dipole is working on the harmonics. This is 2 lambda.